So I'm going to kind of go fast through some of this because we already covered some of this right before we did the lab on Friday. And some of this I've just mentioned as we've gone through other parts of the notes. So I think we can get through this fairly quickly. We're going to try and get us to the Aufbau diagrams and the maybe electron configurations today. We'll see how far we get. So we're on, again, Roman numeral number 3, atomic spectra. Okay. So white light, we talked about this on Friday. White light is made up of all the colors of the visible spectrum. Okay. So when you see the white light coming out of those fluorescents right there, what you're really seeing is all the colors of the rainbow, but they're all kind of blended together so that your eyes can't separate them. If you pass them through a prism, like the picture here, that splits the light into its different wavelengths so you can actually see each of the individual colors, but they're all there. Okay? That says prism. Passing through a prism separates them. Oh, that's not one of your blanks. Okay. If the light is not white, then what you end up with is something that looks kind of like this picture. Okay? Now notice there are gaps in the spectrum. Okay, so it doesn't look like a rainbow anymore. You see distinct lines of color, like you saw through the spectroscopes when we looked at the gas. You guys remember that from Friday? Okay? So it does something different when we pass this light through a prism. Okay? Each element's going to give off its own characteristic colors. And those colors can be used to actually identify the atom. Okay? Now, I think this is really cool. Number 3 here, it says this is how we know what stars are made of. It's pretty impressive to me that we can know the chemical composition of something that's billions and billions and billions of light years away. But all we have to do is look at the light coming from a star. We pass it through a prism. We see those distinct lines of color, and because each of those lines of color are unique to a specific element, we know exactly what elements are in those stars. Okay? So, kind of a cool thing. So here's some examples of atomic emission spectra. Okay, I think the one that we looked at was mercury, and I don't think mercury's is up here. I believe this one at the bottom down here is hydrogen. Okay, but these are some different atomic spectras, and they're just called atomic emission spectrum. Okay, because it's the wavelength or frequency of light that those atoms are emitting, giving off. And again, these are unique to each element, kind of like a fingerprint for the element. Okay? So we can look at it and we can know exactly what element that is. And so it's very useful for identifying elements, for example, figuring out what elements are in the stars. Okay? Today we will, well, this happened Friday because I got a little excited and wanted to show it to you on Friday. But we looked on Friday at a piece of equipment called a spectroscope. Okay? And there's really not a lot to it. You're basically just, it's a prism with some number measurements on it so you can see the wavelengths of light that you're looking at. Okay? And it says we'll look at 3 different elements. We only looked at the one. We looked at mercury, I think. Okay? And we also have some 3D glasses available that we didn't have time to play with, but they're kind of cool because you put those on and they do kind of the same thing that the spectroscopes do. And we're not doing any calculations with this, okay? But you can actually, based on the wavelength that you find, you can calculate the frequency. That's what the V stands for, is frequency. And you can calculate the energy of each of those lines of light. So you can figure out, based on that wavelength, you can figure out how much energy the electron is losing when it's dropping from one energy level to another, okay? Which I think is kind of cool. You can figure out exactly what those electrons are doing, how far they're falling, and how much energy they're losing. But we're not going to do those calculations. I just want you to understand it conceptually. Okay? So an example here, red light has a wavelength of 6.50 times 10 to the negative 7th meters. How much energy does this photon carry? Okay. And again, we could figure this out. There's a formula, C equals wavelength times frequency. That's the speed of light. That's the wavelength, that's the frequency. The speed of light is always the same. It's 2.998 meters per second. Okay. The wavelength here is 6.50 times 10 to the negative 7th meters. So then all we have to do is solve for V. Okay. It looks complicated, but it's really not that bad. Whoops, 2.998. That's a little slow for light. Times 10 to the 8th meters per second. Okay, so then you can solve for the frequency, and then once you have the frequency, you can plug it into this equation right here, and you can figure out the energy of that particular light. Okay, so that's how you would do that. All right, flame tests. So we also did this on Friday. Okay. I'm not sure why the Heisenberg uncertainty principle is under the flame tests. Other than, I guess, Bohr was never able to really explain the flame test, so we needed the quantum model for that. Okay, so we've talked a little bit already about the Heisenberg uncertainty principle, so now you're just getting it in your notes. Okay, Heisenberg said that it was impossible to know exactly the location and velocity of an electron. By the way, this is making Breaking Bad make more sense to some of you. Oh, that's why he picked the name he picked. It's because Heisenberg. Yeah, okay, if you haven't watched Breaking Bad, you don't know what I'm talking about. Oh yeah, his code name is Heisenberg, right? Yeah, because of the Heisenberg uncertainty. That's why he picked it. Yeah. Anyway, so it's impossible to know exactly where an electron is and how fast it's moving at the same time. Heisenberg said that this is not just a problem with the equipment that we have. This is actually a fundamental limit in nature. We will never, ever be able to know exactly where an electron is and how fast it's moving at the same time. Okay? The more we know about its velocity, the less we know about location. And the reason for that, again, remember, if we try to measure the electron, the only way we have to do that is to hit it with light, right? But you hit the electron with light, what does it do? It moves, okay? The electron moves because the light gave it some energy, and so now the electron jumps up to a higher energy level. So it's not where it was, okay? So we can kind of know where it was, but we can't know where it is. There's Heisenberg. And I guess he's talking right now, which is weird because he's dead. But one cannot simultaneously determine both the position and momentum of an electron, okay? You can find out where the electron is, but not where it's going, or I guess vice versa. You can find out where the electron is going, but you don't know where it is, okay? So that's just a problem with our measurements. Okay, so this is again why, okay? So I'm going to go through this fast. To measure where an electron is, we use light, but the light energy moves the electron after hitting the electron, and hitting the electron changes the frequency of the light, okay? So now both of the things, when they've collided with one another, they've both changed. So now we can't really know where the electron is anymore. Okay, so then the Bohr model. Oh, okay, this is a diagram of the Heisenberg uncertainty principle. Okay, so you hit the electron with a photon of light. Okay, the photon of light hits the electron, and the electron moves, and the photon wavelength changes, and so now everything's off. Okay. This is a picture we use a lot. You just need to know that this isn't entirely correct. We don't have a good way to represent this. Really what happens is the electron sort of pops out of existence here and pops into existence somewhere else, okay? Which is very strange, but that's how quantum jumps work. An electron is one place, and then all of a sudden it's not there. It's instantaneously somewhere else, okay? So it's not like hitting a pool ball on a pool table, where you hit this thing and they both kind of go off in their separate directions, and you can watch their paths in either direction. Okay, the electron, it's just like you hit it and it's gone. And where did it go? Somewhere else. Okay, so electrons are weird. All right, here's Niels Bohr. His model, the atom. He kind of took his idea from Rutherford. Rutherford said that the electrons orbit around the nucleus, and so he used that. But he kind of went one step further, and he basically said it's the rungs of the ladder thing, okay, that we've been talking about. So now you're just writing that down. But the energy level of an electron is analogous to the, oh, I'm not to that part, sorry. But basically the electrons are in a certain energy level, and they can jump from one energy level to another energy level depending on the amount of energy they have, okay? And the energy level of an electron is like the rungs of a ladder. The electron can't exist between the energy levels, just like you can't stand between the rungs on a ladder, okay? And then he, along with a couple other scientists, defined quantum as the amount of energy that's needed to move an electron from one energy level to another. Another scientist coined the term quantum, but he used it for atoms. Okay? So that's basically exactly how much energy it takes to make that electron jump up to a higher energy level. Okay, and then we got the quantum model. Quantum model says energy is quantized, comes in chunks. Okay, in other words, there's not a continuous amount of energy that you can supply to something. You give it little bursts of energy. Okay, that's the amount of energy needed to move electrons from one energy level to another. Okay, so since the energy of an atom is never in between, there must be a quantum leap in energy. Schrodinger derived an equation to describe the energy and position of the electrons in an atom. Okay. I don't know how far we got on that video. Had we talked about Schrodinger versus Heisenberg? Were they talking about that yet? I think Heisenberg, right when we had to stop, Heisenberg was about to go to Schrodinger's lecture and challenge him and say, hey, your ideas are dumb. And then everyone ridiculed Heisenberg and, laughed him out of the place. But then he proved them all wrong. So basically, Schrodinger and Heisenberg had this, they didn't like each other at all. And the funny thing is, Heisenberg ended up using Schrodinger's equation kind of against him. Said, hey, this Schrodinger equation, that we can actually use that for our model, but he used it for a different reason than Schrodinger used it. But basically all it does is it describes kind of where, it describes those orbitals. You remember talking about the orbitals? Okay. So the orbitals are like this room, right? If I'm standing outside the room and I've got something over the door so I can't see in, all I can say is, you're in this room. That's what we can say about electrons, okay? So Schrodinger's equation basically defines those orbitals, those regions where electrons probably are. And it's probably better that you can't see that. Any mathematical equation with a pitchfork in it is just, not a good mathematical equation. You're going to end up having to do a lot of calculus. I wouldn't even worry about that too much. Do you have to? You don't have to fill that in. Okay. Okay, so the orbitals, all right? The principal quantum number is basically the energy level of the electron, okay? So that corresponds to, if I'm going to draw Bohr's model, which Heisenberg wouldn't like me doing this right now, so sorry, Heisenberg. But this is maybe the first energy level right here. This is the second. This is the third, okay? That's not exactly right. The quantum model doesn't work quite that way, but in a simplified Bohr model, that's kind of the idea, okay? So the electrons that are closest to the nucleus, they're in the first energy level, okay? They have an energy level, principal energy level of 1. Okay, the electrons that are in that second energy level have a principal energy level of 2, and then 3. And so on. It goes all the way up to 7. Now, the cool thing about this, you're not going to be able to see this on the video, but these energy levels actually correspond to the rows on the periodic table, okay? So hydrogen and helium only have electrons in the first energy level because they're in row 1, okay? Lithium, beryllium, all the way to neon, their outer electrons are in the second energy level because they're in row 2, okay? Sodium all the way to argon, their outer energy, or their outer electrons are in the third energy level. 4th, 5th, 6th, 7th, okay? The ones at the bottom actually belong here. If you could get up close to this enough, you would see that there's a gap between 57 and 72. These really should be right here, but my periodic table would be way too long. So the way that it's typically done is these two rows are kind of removed and put down below, just so that the periodic table is not, you know, impossibly long. So they'd be in the 6th and 7th, yes. Okay? So that's kind of how that works. If we ever discover another electron past UU, or not another electron, sorry, another atom past UUO, it would be in the 8th energy level. It would have its outer electron in the 8th energy level. It would be very unstable, too. Okay, so these are called atomic orbitals, okay? Regions where there are high probabilities of finding an electron. So you have to write down the part after the parentheses here. Regions where there is a high probability of finding an electron. Okay, and what scientists started to find was, if you're looking at the periodic table, there are actually sub-levels, okay? So the general category here for sodium all the way through argon is that they're in the 3rd energy level, okay? But some of these atoms have electrons that are in lower energy orbitals, and some of them have electrons that are in higher energy orbitals, okay? I like to use the hotel analogy for this, okay? And I think it's going to make more sense if I just show you the hotel here, okay? So these are the 4 different sub-levels you can have, S, P, D, and F, okay? You could say it's like theater seats arranged in sections, or you could say it's like rooms that cost a different amount on the same floor of a hotel, okay? So you go to a hotel, right? You got the first floor on the hotel, but some of the rooms might be like the deluxe, the suite rooms, right, on the first floor. And then you've got the second floor, same thing. Okay, so they might cost different amounts depending on how nice the room is. Where are we here? This isn't on the notes, is it? Okay, so this is basically what I just drew. N equals 1 for the first energy level, N equals 2 for the second, 3, 4. Whoops. And the maximum number of electrons that can fit in an energy level is, and I'm not too worried about this formula either, because I think I want to just get to the Aufbau diagram. Okay, here we go. This is the atom hotel. Okay? There's a couple of things you need to understand about electrons. Okay? This is really, really important that you hear me on this because this is going to help you. All right? Number 1, electrons are cheap. Okay? They will take the cheapest room available to them. Period. When they're coming to the hotel to stay. Second thing you got to remember about electrons is they're a little bit antisocial. They don't like to be around other electrons if they can help it. Right? Now, in reality, they're not really antisocial. They repel one another. Why does one electron repel another electron? They both have a negative charge, right? And if two things have the same charge, they repel, right? So electrons don't like to be around other electrons if they can help it, all right? So the way this is going to work, you kind of have to pretend a little bit here that this is happening because this isn't exactly what's happening. But let's say that an atom is being built, okay? And so the electrons are coming into the atom here to build the atom. And let's say we're building a, I don't know. Well, let's start with hydrogen, okay? Let's say we're building a hydrogen atom. How many electrons in a hydrogen atom? You guys can do this. How many electrons in a hydrogen? Just one, right? Okay, one electron. So remember, electrons are cheap and they're antisocial. So where's that one electron going to go? First floor is the cheapest floor, all right? So the electron's going to go down here. Now, the way that we usually draw this is we make a little up arrow, okay? I'll show you why we make an up arrow in a second. That's going to be hydrogen, okay? Now let's say that we're done with hydrogen. That's it. Okay, that one electron is there all by itself. Okay? Not a bad deal for that electron, I suppose. Helium is the second element on the periodic table. How many electrons does it have? 2, right? Okay? So we've got that second electron coming in. He wants a room in the hotel. I don't know why he's a he. It could be a she, but the electron comes in, wants a room in the hotel. Where is it going to go? Well, the question is the electron more cheap or is the electron more antisocial? And the answer is the electron is more cheap than it is antisocial. Okay, that's important to remember as well. So the electron will take the cheapest room even if it has to share a room with another electron. Does that make sense? Okay? So it's going to go here in this first floor. Okay? Right there. Now, the way that these electrons get away with being in the same place, they really don't like each other, but one electron says, all right, fine, I'll spin this way, you spin this way. Am I doing that right? Okay. This is something that's really going to mess with you. It's really hard to get both of your hands spinning in different directions at the same time. Okay? Let's see if I can do it right now. This is really hard, okay? To get them spinning in both directions. You're going the same way, see? Feels like you're doing it differently, but you're not. This is really, really hard. Yeah, you really got to think about it. See, it's difficult, isn't it? I was very surprised the first year I tried to explain this. They're like, yeah, your fingers are going the same way. And I couldn't get my hands to go opposite ways. So, you know, if you get bored later and you want something to do, you know, you can try that because it's very difficult. All right, anyway, here's my point. These electrons end up spinning in opposite directions, okay? So one electron will spin, we call it the up spin, and the other electron will do a down spin. If they're spinning in opposite directions, they're okay with being in the same room, okay? That's the only way that they'll do it. So that's why we use an up arrow and a down arrow to show them. Now, another thing you need to understand, only 2 electrons per room. All right? That's the maximum number of electrons in any given room. Does that make sense? Helium does have 2 electrons, and there they are, right there. Well, okay, now we're talking about helium now, right? So hydrogen only had the 1. So then I moved on to helium, okay? So now let's talk about lithium, okay? So lithium, if we're building a lithium atom, first 2 electrons go here, right? But lithium has 3 electrons, so where does the third one go? Well, it has to go here, right? That electron walks in and says, hey, I want the cheapest room we've got, and the cheapest room is on the second floor, okay, right here. It's called the 2s orbital, okay? So that's where the third lithium electron will go, okay? Now, the there is no fourth lithium electron, but if we're talking about beryllium, the 4th element, where is that electron going to go? Is it going to go here, or is it going to go into the 2p's? These are both on the second floor, right? These both have the number 2. What's the difference between the S's and the P's? Yeah, the S is cheaper, right, because it's a little bit lower down on the energy diagram. So this is like the basic room for the 2s and then the deluxe rooms for the 2p, right? So this electron is cheap, right? So it's going to go into the 2s orbital for beryllium, okay? I'll just go, phosphorus, that's kind of far away. We'll just go to the second, into the second energy level. Okay, so boron. Boron would have these 4, right? But boron has 5 electrons, so where's the next one going to go? In the 2p. That's the next cheapest room, right? Okay, now, here's where it gets a little tricky. You get to carbon, okay? Carbon has 1 more electron that it needs to put somewhere. Where's that electron going to go? Remember, they're cheap and they're antisocial, okay? So the next electron walks in, and these rooms all cost exactly the same, right? So the next electron's like, well, why not get my own room, right? Okay. And then the next electron that comes in when you're building a nitrogen, now you've got your 7th electron you have to put somewhere. That's going to go right here, okay? So that's the orbital diagram for nitrogen. Okay. What was your question, Kelsey? You forgot? You said something about antisocial. How do you know they're antisocial? Because they're both negatively charged, right? They don't like each other because they both have a negative charge, so they're going to repel. Okay? So that if they can be in different orbitals, they will be. Okay? Just think of the orbit. How do you know which ones are like that? Okay. When you have 3 like this that are all exactly the same energy because they're on exactly the same level, that's when this is going to happen, okay? It's going to happen here. It's going to happen here. It's going to happen here. Because there's only one box there, right? So this 1s right here, there's only one place they can go. These are the cheapest rooms right here. They don't have any other options, okay? So you've got, let me back up here for a second. So you've got a setup like this, right? If the second electron's coming in, it can either go here, or it can pay extra for a different room, right? But it has to be a much higher energy to go to the 2s, okay? So it's going to choose to go into the 1s, because there's a cheaper room available at that point, okay? Here, when we're talking about the 4th electron coming into an atom, okay? It could either go here, or it could go here, right? But again, this is the cheaper option, okay? This is the cheaper room, so it's going to go there. Once you get up to here, now the electron can choose to be in a room with another electron, or have the same amount of energy and be in a different room. So it's going to choose that, okay? Everything up to that point, it would have had to jump in energy in order to be in its own room, okay? But here, because the energies are the same, they'll go in separate rooms, okay? Then what do you think happens once we get to oxygen? Now we've got 8 electrons, so the 8th electron has to go somewhere. Where do you think it's going to go? Is it going to go into the 3s? Okay, the 2p rooms are still cheaper than the 3s rooms, right? So the next electron will go right here. Okay? Okay? And then the fluorine, the next one, number 9, the 9th electron, is going to go right here. Fill up that room. And then the 10th electron is going to go right here. Okay? Now, do you guys remember in, we're not going to really talk about this until second semester, but do you remember in 8th grade talking about the fact that the noble gases are stable and everything kind of wants to be like the noble gases? Did you guys talk about that? Some of you are saying yes. The reason why is because this is a fairly stable configuration here. All the rooms in the first and second energy level are full. Okay? That's stable. And that's going to happen anytime you have a noble gas. Okay? So that's kind of the idea here of how these fill. All right? Okay. Now let's take a look at the order that the orbitals get filled in. Now, you don't have to memorize this, okay? Because you're going to have, I'm going to give you one of these that you can use for the test, okay? Because I don't really care that you memorize this. What's that? You might have to fill one of these in on the test, yeah. Okay?
Are all the boxes just moving one arrow up and one arrow down?
Yeah, it just depends on how many electrons we're dealing with, right? So, well, we'll see. I'll show you an example of one in a minute. Okay, so here's the order for filling the orbitals. It goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, blah, blah, blah. Okay? See, I'm a little torn here, because the thing is, you probably are going to have an Aufbau diagram on your test, which means you could look at the Aufbau diagram and that would tell you the order, right? And there's a way that you can know it from the periodic table, okay? These first two, well, what you have to know from the periodic table is there are certain blocks of elements where you're filling either S or P or D or F orbitals, okay? So if you look back at the Aufbau diagram, notice in the hotel here, you've got your 1s, then you've got 2s, 2p, then you've got 3s, 3p, 3d, okay? 4s, 4p, 4d, 4f. You see how each energy level you add another set of suborbitals, okay? You add a new shape, basically, okay? And so what you can do here when you look at the periodic table, you can say, and this may or may not work for you, but I'll just show it to you, okay? All of these right here, their outer electrons will be in the s orbitals, okay? All the ones on the far left. All the ones on the far right here, in this block of 6 here, their outer electrons will be in the p orbitals. Okay? All the ones in the middle, their outer electrons will be in the d orbitals, and all the ones down here, their outer electrons will be in the f orbitals. Okay? So you can kind of remember the order if you remember that. So this is the 1s right here, and then these are 2s, 2p, 3s, 3p, 4s. No, I didn't. Actually, 4s and then 3d. It's kind of weird, okay? But the d's don't start till right here, and they go down a level, okay? So 4s, 3d, 4p, 5s, 4d, 5p, okay? Here's where it gets really weird. So now you've got 6s. Then you have to jump down here to the 4f's. And then you've got 5d and 6p, okay? And then 7s, 5f, 6d, 7p, okay? Maybe what we can do tomorrow is label a periodic table with those areas on it, and I think that might help you out, okay? But that's the order. And again, I don't necessarily expect you to memorize the order. Like I said, if you get an Aufbau diagram on the test, then you're going to know the order anyway, because all you have to do is look at this, right? And you can say, okay, the 1s is going to fill first, then the 2s, then the 2p, then the 3s, then the 3p. Then you got to be kind of careful here. The 4s is a little lower than the 3d. Does everybody see that? Okay, so then the 4s, then the 3d, then the 4p. So you just look at which energy level is the highest, and it will fill in that order. It goes from the bottom to the top.
So it goes 5s, then 4d.
Yeah, 5s, 4d, 5p, okay? And then 6s, 4f. And that's where it gets a little bit hard to tell what is higher than what, okay? But I'm not going to give you any that really get up that high anyway, okay? We're going to keep this fairly simple since we're at the end of the semester here. But the electrons are going to fill up according to that order. It follows the Aufbau diagram from bottom to top, okay? So some examples. The example seems to not be... Okay, you have it in your notes, though, so let's just go back to the Aufbau diagram and do phosphorus here, okay? How many electrons in phosphorus? Number 15 on the periodic table, so there's 15 electrons, right? So we've got to put 15 electrons in the hotel, okay? So first two are going to go in the 1s. Does that make sense? 1, 2. The next two will go in the 2s. 3, 4. Okay, now, okay, thank you. Now pay attention here. 5, 6, 7. See how I did that? Okay. 8, 9, 10. How many do we have to go up to? 15? Okay. So then 11, 12. Where am I going to put the next 3? Okay. 13, 14, 15. Right? That's the orbital diagram for phosphorus. That's what it's going to look like. Does that make sense to everybody?
You do the same thing when you get to 3D. Would you go all of them up?
When you get to 3D, you do the same thing. You know, if you had, and that's going to be, I think that would be manganese, Mn number 25, would be the one where you end up with all of the arrows pointing up. Okay, but then you would go back,
And go down.
if you were talking about something like zinc, and you would fill them all in. Okay? So you just think about the number of electrons you have, and think about the rules for filling this hotel. Okay? Now, the technical rules are called the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Okay? But I just taught those to you by telling you that electrons are cheap and they're antisocial. So as long as you remember that, you will remember those 3 rules. And I don't care if you remember the names of those people and their rules. Okay? You just need to know that electrons are cheap and electrons are antisocial, and that's why they do what they do. Okay? Let's see, what time is it? Okay, we probably should go ahead and stop. That's a good place to stop. And then we'll talk about electron configurations first thing tomorrow. No quiz tomorrow because I want to do orbital notation and electron configurations at the same time on a quiz. All right?
Quiz, we're going to be one of the first.
Okay, hang on.